Hey, Science 10s, this is CA7. If you haven't watched the other videos up to this point, go back and do it. So this is looking at molecular compounds naming notes. So CA7 in your booklets. You should have done all the worksheets up to this point, and then you will have a worksheet for this one. So chemical compounds. So a compound is a collection of two or more elements in a definite composition. So the forces that hold the elements to each other inside the compound are known as chemical bonds. So a compound may be classified as molecular or ionic. So we did ionic already, so let's kind of talk about that. So a compound is ionic if electrons are transferred from one atom to another. And so again, that's the formation of ions. And so a molecular compound is different in that no ions are actually formed. What's actually happening is the electrons, oh my gosh. Okay, come on. Oh no. Electrons are actually shared between atoms. So instead of something giving up an electron and something accepting an electron, what's actually happening is they're just sharing them. They're both holding on to things. So this is what we're talking about with molecular compounds. So that'll be today. So molecular elements and compounds naming. So molecular compounds are usually made up of two or more non-metallic elements. So that's on top of or to the right of the staircase. So all of the things up in your top corner there. So you've probably colored that in your periodic table. It's all the ones above the staircase. So some examples that we have are CO2 or CH4. So we'll talk about what those elements are. So we're going to look at CH4 here first. So we know this C is an element symbol for carbon. This H is an element symbol for hydrogen. This 4 subscript, which we talked about in the last one, indicates like how many that there need to be 4 hydrogens. Since there's no subscript here, that tells us that there is 1 carbon. It's not 0 carbons because we wrote the letter C there. There are 0 magnesiums because we didn't write magnesium, but since we wrote C there, there is 1 carbon. So this is actually, oh, it's bad because this isn't a good naming one, methane. We'll talk about a different way that you could name that. But it has a general name, just like sodium chloride we usually just call table salt. This is a general name for what CH4 actually is. So methane, so this is a bad example because it doesn't have the nomenclature that we'll be using, but each methane molecule oh my gosh, I don't know what's going on with my smartboard other than it's so haunted. So last lesson I said not using molecule for ionic compounds. We can use molecule for molecular substances. So each methane molecule has 4 hydrogens bonded to 1 carbon. So what's actually happening, I'm going to just try, I'm not going to draw a Bohr diagram, but if you think back to the Lewis dot diagram, so carbon is atomic number 6, so it has 2 electrons in its inner shell and 4 in its valence shell. So what carbon actually looks like as a Lewis dot diagram, carbon looks like that. If I drew a hydrogen, a Lewis dot for hydrogen, hydrogen just actually has 1 electron. So in that inner shell where it could fit 2, it's got 1 of its 2. So I'm going to draw hydrogen. I wish I could do different colors. So I'm going to draw the Lewis dot diagrams next to everything. Can I get rid of that? So if I look at 4, it's really nice if you have different colors that you make these hydrogens and their electrons blue and the carbon red or something like that. It makes it so much more clear, but we'll survive. So what's actually happening? This last hydrogen has an electron as well. I'm just drawing that electron on either side so that it looks nice. Oh my gosh, I'm going to sneeze. No, I'll survive. So what's actually happening is now this carbon, remember its valence shell is 1 that can fit 8. So what it's actually doing is it is accessing its 4 electrons and the 4 electrons from each of those hydrogen. So you can see that it has access to 8 electrons. So they are sharing. Those hydrogens are not giving up their electron, but they are sharing it with the carbon. They're both kind of holding hands onto it at one time. And each hydrogen, we know hydrogen, it's in that first shell, first energy level, it only has room for 2. So each hydrogen is also kind of borrowing from the carbon as well. So each hydrogen has access to 2 electrons to fill its valence shell. And so this is not electron transfer. It's just sharing electrons. So those electrons don't really belong to the other thing, but they're just kind of saying, hey, you can hold on to this if you need to as well. So electron sharing is what's actually happening there. And so hopefully you can visualize that as well. So some properties of molecular compounds. So can be solid, liquid, or gas. Oh my gosh. I don't know how to fix this. Can be solid, liquid, or gas at room temperature. With ionic compounds, we said very typically they are solid at room temperature. These non-metallic are non-metals, so non-metallic atoms share electrons. And form a covalent bond. So a covalent bond is different than an ionic bond because it's not held together by those electrostatic charges of ions. It's just held together by that sharing. So most of them have low melting points, meaning again, they'll become gases at lower temperature, they'll become liquid at lower temperatures. So the intermolecular forces are usually weak and can be heated without decomposing. So intramolecular, oh, the sneeze is just like hanging on inside my nose, waiting to scare me, waiting to scare you too, I guess, as well. I'll try to cover the mic if I sneeze. So they can be heated without decomposing. So the intramolecular forces within the covalent bonds are strong. That's not something you really need to know about because, again, we're not going to go in as much detail right now. Unless you go into Chem 20, you'll need to look at intermolecular versus intramolecular forces. Most do not conduct electricity as pure substances. Some will if they form ions in solution, but like I was saying last lesson, if I dissolve table sugar or sucrose in water, they don't actually form ions, but most of them do not conduct electricity. So says, why do elements form bonds? So it says, recall, elements are most stable when their valence shell is full. In order for some elements to fill their valence shell, they bond with other elements by sharing electrons. So this is exactly what I did for that methane on the last page. Same idea with water here, actually. So H2O. So Bohr diagram for hydrogen and oxygen. So our Bohr diagram for hydrogen, oh my gosh, this is not very much room, especially when my pen is a piece of garbage right now. I don't know what's going on here. 1p. Oh my gosh. Holy moly, I don't know what's happening here. If I drew out, I think what I'll do, this isn't going to really help, just based on my notes package or my key, I will try this for a bit. So if I drew my Bohr diagram of hydrogen, again, 1 proton, 0 neutrons, so it would have 1 valence electron in that shell where there can be 2. And if I drew oxygen, sorry, this electron should be crossed out. I'm just gonna kind of, oh, it won't let me do anything. My darn computer. Sorry, this one, just draw it properly. There's 1 extra electron where my cursor is right now that you actually don't need to draw in. So 8 protons should be representing 8 electrons for an oxygen atom. So it says, let's look at how bonding allows them to fill their valence shells. So we know H2O, so there's 2 hydrogens, 1 oxygen. So if we kind of line it up, you can see the different colors. I had pink and blue, but it's black and white on my scan. So these 2 electrons, oh my gosh, all the technology is falling apart at once, of course. So here we had, maybe if I take it off this, nope, this. So this electron, nope, still won't do anything. We know that there are room for 2 more electrons in oxygen, so it will share with the hydrogen here and share with the hydrogen here. So in total, this oxygen has access to 2, 4, 6, 8 in its valence shell, and this hydrogen has access to 2, which is all that it needs in that first shell, and this hydrogen has access to 2, which is all that it needs in that first shell as well. So that's the Bohr diagram of H2O altogether. So not just an element, but everything. Again, there are no ions formed. It's just sharing of electrons, forming of covalent bonds. So that's where the covalent bond would be. So naming molecular compounds. So molecular elements. This is in your periodic table. It's up kind of above nickel and copper. There's a little box there that says polyatomic elements. So these are elements that are on their own that don't naturally exist as single atoms, so instead they pair up. So it says diatomic molecular elements are the ones that don't exist naturally as single atoms because they're very unstable, so they exist as a pair. These molecules are composed of 2 identical nonmetal atoms. So this group includes group 17, so all those chlorine, fluorine, bromine, iodine, things, and also oxygen and hydrogen, nitrogen, where's nitrogen? Oh yeah, nitrogen as well. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and also hydrogen. So it looks like an upside down hockey stick is the analogy. It looks like a 7 to me. And hydrogen, but again, it's in your periodic table, so you don't need to memorize which ones they are. So all of your group 17 are diatomic, so di meaning 2 here. And then you see there's 2 others. So phosphorus, on its own, it's not really very happy. It actually doesn't bond diatomically to itself. It's polyatomic. So P4 is what you'll usually see when it's on its own, when it's in its elemental or atomic form. It actually wants to be as P4. Sulfur gets really lonely. Sulfur is not great at social distancing, and sulfur actually forms S8 when it's on its own. So those are molecular elements, and those are important to kind of keep in mind when we start writing chemical formula. You need to keep track of those. So on its own, oxygen wants to form O2. Oh, I guess it has a question like that below. So an example, it says, write the formula for bromine. So bromine is one of our diatomic elements, or our polyatomic, poly meaning many, diatomic meaning two. So the formula for bromine would be Br2. Formula for oxygen would be O2. F2 we would just call fluorine, N2 we would just call nitrogen. Because again, it's kind of accepted that they will be found in that form most often. So that's molecular when it's just made up of one element. Yes, there's more than one piece to it, but it's just made up of one element. When we get into binary molecular compounds, that's two different. Yeah, it doesn't let me do anything in here. Maybe because I'm recording? I don't know. So these compounds are composed of two different non-metallic atoms. Again, still looking above the staircase. So steps for naming binary molecular compounds is you write the entire name of the first element, again, lowercase and spelled correct. So the first element that's in your molecular unit or your formula for it, you name that first, the whole name, the whole regular name, and then you change the ending on the name of the second element to IDE, as your periodic table tells you how to. And what you do is you add the appropriate prefixes based on the subscripts of it. So the example that I'll use instead is up to here. CO2. So based on those rules that are on that other page, so again, it says write the name of the first element. So the first element is carbon, so you write carbon. And then the next element is with the IDE ending. So it's oxygen, so it would be oxide. So carbon oxide, but we need to think of our subscripts. So this subscript of 2 is related to our oxygen. So we put a prefix in front of oxygen to say that there are 2 oxygens. So the way that we would name that, let's see if it'll let me do this now, is, oh my gosh. Oh. I like that it's making my writing way better. So carbon, and again, the other word was oxide. Oh, it was so good for a second. So carbon oxide, but now we need to think about our prefixes. So prefixes, the word pre means before. So prefixes for our subscripts. So we know that 2 is di, so we're going to put that in front of the word oxide. So carbon dioxide. You've heard that before. That's what you breathe out when you are breathing out. You're breathing out a lot of carbon dioxide, and it's coming out of cars. And it's when you're heating your home, you're producing carbon dioxide. You'll notice that there is a prefix for one of something, so we use the word mono for that, but this little part here, it says if one atom is present for the first element, don't use mono. So we wouldn't call this mono carbon dioxide. You don't need to say that. You just say carbon dioxide, but if you only have one of the second element, so if we had just CO, and it makes my writing look so nice. We wouldn't name that, again, if there's only one of the first element, you don't put mono in front of it, but in this case, there's one of the second element. So I guess, oh, it won't let me erase. You might feel the need to say monoxide, and I would never mark that wrong because again, it's the word oxide and we should be adding a prefix of mono in front of it. But when you have the double O, you usually just get rid of one of the O's. So instead of carbon monoxide, it's carbon monoxide, which you also may have heard of. So carbon monoxide is a product of incomplete combustion. So if you have a furnace that's not working quite right, it's not getting enough fresh air intake, your furnace actually will start producing carbon monoxide. And you've heard of carbon monoxide poisoning. Carbon monoxide binds irreversibly to hemoglobin in your blood, and it's basically suffocating you without you really knowing, because your blood can't pick up oxygen to get oxygen to your tissues. So that's carbon monoxide. So you can see the importance of having the prefixes. Carbon dioxide, yeah, that's fine. You can breathe in carbon dioxide and you'll just expel it right back out. Your body has lots of carbon dioxide in it. It's trying to get rid of it, but it's not going to kill you to have some carbon dioxide go into your body. If you have lots of carbon monoxide going into your body, though, you are actually going to die. It bonds irreversibly. You basically won't be able to breathe because you can't get oxygen to your tissues, and oxygen is necessary to keep your brain going, to keep your heart going, to keep all your muscles going. So it will suffocate somebody. Get a carbon monoxide detector if you don't have one. So prefixes for molecular compounds, you'll need to kind of write these into your notes. They are in your data booklet, I believe, but you'll get so used to using these ones. Actually, I don't know if they are in your data booklet, but you'll be able to access them with your notes anyways. So mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and 10 is deca. So the example that they have there is Cl4. So C is carbon, you just name it as is. Cl4, so there's 4 chlorides. So the way that you name that is carbon tetra. So tetra is for 4. So carbon tetrachloride. So the ending IDE, the prefix here, carbon tetrachloride. Another example, SO3. So again, when you only have one of the first thing, you don't use mono. So sulfur, and 3 of the oxygen, so oxide. 3 is tri, sulfur trioxide. P4O10, ooh, big one. So P4, so now we don't just have one of the first element, we have 4, so we're going to use our prefixes. 4 is tetra, so tetraphosphorus, deca, deca is 10, deca oxide. All right. So steps for writing the chemical formula. This is actually, I usually find molecular formulas easier than ionic, because you just have to look for those prefixes to figure out how many of things there are. So write the symbols for each element in the order that they appear in the compound name. Use subscripts to indicate the number of each atom for each element based on the prefixes. So chemical name, I had to add in, I don't know if I changed it in your notes, it says dinitrogen sulfide. So we use the mono, this, if you can't read it here, it says monosulfide. So it should be dinitrogen monosulfide. So dinitrogen means 2 nitrogens, so N2S, and again, monosulfide means 1 sulfur, so you don't need to put the 1 there. Carbon tetrafluoride. So since there's no prefix on carbon, we know there's just one of them since it's the first element. And tetra means 4, so it's CF4. Oxygen dichloride, again, since there's no prefix on the first one, oxygen, we know there's just one. Dichloride, di meaning 2, so 2 chlorines, so Cl2, OCl2. Nitrogen. So that only has one element, so I would be like, oh, that's a little bit funky. Why is she asking me for just one element? So you need to think back to those diatomic and polyatomic elements. That's what we had on that last page, and it's up in that little box. Nitrogen on its own is going to be found as N2, diatomically. Phosphorus pentachloride, so phosphorus, since there's no prefix on it, we know there's just one phosphorus. Penta, meaning 5, so PCl5. Dinitrogen tetraoxide. So dinitrogen meaning 2 nitrogen, tetraoxide, so tetra is 4, so N2O4. And so something like this one, again, you got to really keep your rules for ionic and molecular separate because they are separate naming systems. You don't reduce this. In ionic compounds, I said if you have something that has like a common factor within it, you would reduce it. But for, uh-oh, don't reduce. I'm going to write for molecular. This is going to say molecular. For molecular compounds, you don't actually reduce it. That ratio is fixed, so you can't change it to just NO2 because that's a different compound. That's nitrogen dioxide. That's something totally different than dinitrogen tetraoxide. So you've got to keep your rules very clear with these two things. So it says, note, there are some common molecular compounds whose chemical formulas you actually must memorize. And so that's on to the next page. And so the first one I'm going to feature is methane. So that's the one that I had on that first page, CH4, and I said it was a bad example because it doesn't really follow our naming scheme. So CH4 you might name as carbon tetrahydride. We actually want to refer to it as methane instead. So the common molecular names are what we're going to work on. So methane is actually CH4. Methanol, oh, and sorry, methane is what goes into your furnace. It's natural gas. It's what burns to heat your home if you have a gas furnace, which most people do, but some people have electrical heating in their homes, so in a lot of apartment buildings, but that's still coming from a gas burning, sometimes it's coal burning, I guess, power plant, but it's a hydrocarbon product, methane. Methanol, so CH3OH, is a wood alcohol. It's poisonous to humans, and it's fuel for drag racing cars. That's interesting. So CH3OH, this one is kind of confusing in that you're like, well, if there is an extra H here, why don't we just make it CH4O? This OH is, it's actually more to do with the structural drawing of methanol. If you wrote CH4O, I guess it's not truly wrong, but this OH indicates that it's actually a hydrocarbon with what's called an alcohol group on it. The OH group is an alcohol group. So writing it in that form gives us an indication of its structural components. So ethane, C2H6, is another component for petroleum products, or part of petroleum products that are being drilled and pumped out of the ground. Ethanol, so again, if you see that ending OL, so C2H5OH. So again, it's got that OH group at the end. And so this is the alcohol of alcoholic beverages. So in beer or wine or something, that's actually ethanol within it. So instead of trying to name this in the wildest way ever, we would just write ethanol for that. So if you come across something that you're like, I have no idea how to name this, just look in this chart because that's probably what it is. Propane, C3H8, butane, C4H10. If you take Science 20, we're going to talk a lot about methane, ethane, propane, butane, all of these hydrocarbons and their uses and how they're extracted. So C4H10 is butane. Acetic acid, so this is actually just vinegar. CH3COOH, so it's a particular group called the carboxylic acid, which we actually deal with in Science 30. But again, these are just ones that you need to have memorized or be able to recognize. So ammonia, NH3, so it's not nitrogen trihydride. You would use ammonia instead. Glucose, C6H12O6. So that's what's produced from photosynthesis and goes into cellular respiration. Hydrogen sulfide, H2S. Ozone. So sometimes in our wonderful atmosphere, kind of beyond where we are, there is something called the ozone layer. So ozone is sometimes found as O3 instead of just O2 because oxygen, sorry, did I say ozone? Oxygen is sometimes found as O3 instead of O2 up in the atmosphere, and it's important for blocking out UV radiation. You guys have heard of the ozone layer before. So sometimes if you see something that's O3, that's ozone. Sucrose is your table sugar, C12H22O11. So really big molecule, right? It's got 12 carbons, 22 hydrogens, and 11 oxygens. There's lots of stuff going on. H2O, please don't name H2O as dihydrogen monoxide. It's water, just write water. And the last one is hydrogen peroxide, so H2O2. You've all seen the bad jokes with somebody walks up to the bar, or a scientist walks up to the bar and says, "Can I have an H2O?" And the bartender gives them water. And then somebody walks up and says, "Can I have an H2O2?" And that man died because he drank hydrogen peroxide. Bad jokes, that's what I'm all about. So memorize this table, and you can now work on the questions that have molecular compounds. So again, recognizing this table of the ones you need to memorize, otherwise naming it with these prefixes and properly. Thanks so much. Bye, guys.